Now I really want to get into studying the asymptotes of a rational function. Okay, and really there are three different types of asymptotes that we could see. We've already seen vertical and horizontal asymptotes, particularly with the reciprocal function that we looked at in the past. Remember, the reciprocal function 1 over x has a vertical asymptote and a horizontal asymptote. Both happen to be at the x and y axes, and the graph approaches them up and to the right and down and to the left. Okay. Other rational functions will have multiple vertical asymptotes. You could have more than one. You could also have, instead of a horizontal asymptote, you could have something we call an oblique asymptote or slant asymptote. Okay, I'll call them oblique asymptotes typically. And an oblique asymptote is one that's basically on an angle. Okay, and so you could have an asymptote on an angle, maybe paired with a vertical asymptote, in which case your graph might approach both of those asymptotes. Okay, and so it's going to look very similar to the reciprocal function's graph, except the horizontal asymptote would be tilted on an angle. Okay, so we have vertical, horizontal, and now we have oblique asymptotes as well. Now what's interesting is that all three of those show up in different ways, and you can find them based upon the equation of the function, right? Based upon the rational expression there. Okay. What I really want to do is get into the behavior at vertical asymptotes, and then we'll look at the horizontal and oblique after that. Okay. So let's take a look at vertical asymptotes. Again, vertical asymptotes, you can have multiple vertical asymptotes in the same function. For instance, if you had any function that has multiple zeros in the denominator that are not shared with the numerator. Remember, vertical asymptotes occur at zeros of the denominator only. All right. So if I had a function, let's say we'll call it g of x is x over x squared minus 25, then here I have multiple zeros in the denominator. In fact, if I factor this out, I get x plus 5 and x minus 5. Now factoring is going to be a very important skill as we move through rational functions and really with polynomials as well. And so I have two factors in the denominator, which means the zeros are -5 and +5, right? -5 from this one, the +5 is from this one. Okay, it's always the opposite sign of what's in the parentheses. And so that tells us, and because neither of those are zeros of the numerator, I should make sure that that's true, then that tells us, right, the zeros, starting a sentence and not finishing it, the zeros at the top are, well, just 0, there's only one of them. And so as long as there's no duplicate there, the 5s are not included on top. So they're zeros at the bottom only. And that tells us that the vertical asymptotes are at -5 and 5. Okay, so that gives us two vertical asymptotes on this graph. Okay, now typically when we have this situation, a vertical asymptote, you will find that the graph will approach the vertical asymptote going upward on one side and going downward on the other. That's what we had with our reciprocal function, and that's what we would have on these. Okay, remember the reciprocal function. I could plot that out real quick here. On one side of the vertical asymptote, the graph is going up toward it. On the other side, the graph is going down toward it. Really on both sides it's a decreasing function going down to negative infinity and then coming up from positive infinity going down, okay? Now that's not always going to be the case. There are times where your graph might approach the asymptote in the same direction, either both sides going up or both sides coming down. Let me show you when that could occur. A very basic example would be something like 1 over x squared. Okay, again, another kind of basic rational function, but still an important one. When I square the x, the outputs are always positive. Okay, so it won't matter whether I plug in a positive x value or a negative x value, the outputs are positive. With the reciprocal function, if you plug in a negative, you're going to get a negative out. Or if you plug in a positive, you get a positive out. But with a squaring function like this on the bottom, both are going to be the same sign. Okay, and so what you'll end up with here is a graph that approaches the vertical asymptote, both sides going upward, okay, and it'd be a mirror image of each other. Okay, now if I were to reflect that across the x-axis and multiply it by a negative, of course that would make both sides go down. Okay, it flips everything to the negative side. So you can have both sides going up or both sides going down. The key on this is that you're going to have an even multiplicity. Remember, we studied multiplicities with polynomials. With polynomials, if you have an even multiplicity, then the graph touches the x-axis and then turns. It doesn't go through. Well, with rational functions, if you have an even multiplicity in the denominator, then you're going to have a vertical asymptote where the graph approaches in the same direction, either both going to infinity or both going toward negative infinity. Okay, so to summarize this a little bit, and of course if you had an odd multiplicity like a 1, then you're going to have this situation where you're going to have the graph going in opposite directions, one up to infinity, one down to negative infinity. And of course, if I multiply that by a negative, it flips the whole thing, and you have the one on the right going to negative infinity and the one on the left going up to infinity. So it all depends upon the leading coefficient as well. So for polynomials, or I should say for x-intercepts and for vertical asymptotes. Okay, so two different categories of zeros, right? In the numerator or on a polynomial, you're going to have x-intercepts. In the denominator, you're going to have vertical asymptotes. And if the multiplicity is even, okay, with an even multiplicity, the x-intercepts are going to touch, or the graph is going to touch at the x-intercept. And that's true for rational functions too, not just for polynomials. So if you have an even multiplicity in the numerator of a rational function, that gives you an x-intercept where the graph will touch the x-axis. And the vertical asymptotes go in the same direction. So the graph goes in the same direction. So either both sides will go to positive infinity or both will go down to negative infinity. If you have an odd multiplicity on that factor, then on the x-intercept, it's going to go through the x-axis, or it's going to cross. I guess crossing is the word we used in the past. And the graph will go in opposite directions for a vertical asymptote. Okay, so one will go up, one will go down, or the other way around, up, down. Okay. Okay, so the multiplicity on those factors is going to be very important, the exponent on those factors. Okay, now let's take a look at just a real quick example, something where you would see this play out. All right, if I had a function, we'll call it f of x. Let's go to minus 6x plus 9. There we go. So we've got x plus 3 over x squared minus 6x plus 9. Well, this denominator is what we call a perfect square trinomial. It factors into x minus 3 times x minus 3, or the quantity x minus 3 squared. Okay, and you can tell that because the first and last terms are perfect squares, and the middle term is double the product of their square roots, right? So I take the 3 and the x, multiply them together, and double it in the middle, you get 6x. And so what you could get if you factored this is x plus 3 over x minus 3 squared. Okay, the minus, the middle sign here shares the middle sign in the polynomial. And so here I have an odd multiplicity on top, an even multiplicity on the bottom. So what we would have is a graph with a vertical asymptote at 3, because the 0 on the bottom is 3, right? It's the opposite sign. So we have a vertical asymptote at 3. And we have an x-intercept at negative 3, right? The opposite sign. Okay? And then the graph of this thing is going to, because it has an even multiplicity here, on the bottom, the graph is going to approach on both sides in the same direction. So either they're both going up or they're both going down. Now, how do I determine which side they're on? Well, as I look at this, I notice that all the leading coefficients are positive, so that gives me a clue that it's probably going upward. But just a real easy way to make sure that that's the case, I could plug in a number on either side of that vertical asymptote. And as long as it's positive, I know they'll both go up, and if it's negative, they're both going down. So, for instance, I might take the number 2, just an easy number to plug in. If I do that, just find f of 2. Then on top I get 2 plus 3, and on the bottom I get 2 minus 3 squared. Well, the 2 plus 3 is 5, the 2 minus 3 is a negative 1, but when you square it, you get positive 1. And so that output is positive 5. Well, that tells me then that my graph must be going upward on both sides, because it couldn't possibly be going downward, because I can't hit a positive number at 2 and still end up going down. It wouldn't work that way, especially without crossing the x-axis. I already know where all my x-intercepts are. They're at negative 3, so I can't possibly have another x-intercept in here. So if we're up at 5 at 2 here, there's no way it can come back down without crossing the x-axis again, and that would create another factor on top, which we don't have. Okay, so my graph must have both sides going upward. And now on the other side here, I know it's going to come through this point here at negative 3, and because of the odd multiplicity on top, right, this really has a factor with a 1 power on it, then it's going to go through that intercept. Okay, so the graph must look something like this. All right, and of course we can always verify these graphs with our graphing calculator, which I'll grab. And okay, so if I want to plot the graph of this, just to verify that that's accurate, I type this in with the numerator in parentheses. You must put these in parentheses, the numerator and denominator, otherwise your calculator won't read it correctly. So I'm going to put parenthesis with an x plus 3, and then my division, right? And then on the bottom, I'm going to put x minus 3. Oh, again, I need parentheses. And I'm going to hit the squared button so that it squares that one. And so here's the final function on the calculator. If I hit zoom standard, like I normally do to start off, okay, my graph looks something like this. Now I don't have the actual x-intercept, or not x-intercept, the vertical asymptote shown on here. That's okay. These calculators don't plot those, but you can tell there's a vertical asymptote and it goes positive on both sides. My question is, what happens over here? This graph is very tight to the x-axis, and so the calculator can't distinguish between the graph and the x-axis. The pixels are too big. So what I want to do is zoom in there. So I'm going to hit zoom, and I'm going to go down to zoom in. Okay? And then I'm going to scroll this over. I don't know if you can see that. My cursor is moving, and I've got it right close to -3, which I know is the x-intercept. Okay? And I hit enter. And still, the graph is having, or the calculator is having a hard time distinguishing between the x-axis and the graph itself. It looks like it's only coming up on the right. So what I'm going to do is I'm going to shrink my y-axis down. Let's see, I'm going to go to my window. And right now my y-axis is running from -2.5 to 2.5. Maybe I'll change that to like -0.5. I'll just delete those 2's to 0.5. Aha! That seems to have worked. And what you'll see there is that this graph does go through the x-axis at -3. So it's above on the right and it's below on the left. And we did have to zoom in pretty far there to be able to really see that. Okay. So my graph here is probably a bit exaggerated. It would probably flatten out a little bit more, but it's got the right properties to it. It goes through the x-axis and it approaches the vertical asymptote in the same direction, both going toward positive infinity.